This next lesson is on exponential growth and decay. To me, this is one of the first times in this math class, so in Algebra 1, that we are actually going to engage in problems that might feel applicable to you, right? Like a lot of you might sit here like, Mr. Younger, and like I understand I have to learn math, but when am I actually ever going to do this outside of the classroom? Okay, I know you all think that every now and again. Okay, and I get that. Those thoughts are completely valid. Okay, and with a lot of the stuff we do, you may not ever do it again. Okay, I promise there's more value than just learning the math and applying it outside. We're also building fundamentals so that if you do get to more complex math, that allows you to engage in more kind of interesting questions that's math related, you have the skills to answer them. Okay, that's a lot of what just school math is. But this lesson is applicable to every one of you. And that's because exponential growth and decay models a lot of applications dealing with like money. Okay, when you all go to college and have to take out student loans, okay, your loans occur interest, and the way that they occur interest is as an exponential growth equation. The way that you pay it back, same idea. Okay, when you all buy cars, buy houses, okay, all these things that are quickly approaching will model some sort of exponential growth or decay equation. Okay, so understanding the rates and how these equations work, actually applicable outside of what we just do in this classroom. So before we get to some of the applications, these equations are going to take the form of what you see here with the exponential equation. A times b to the power of t. A is the initial amount. B is the multiplier. I also call b the base. It's the base of the exponential term, right? Where the exponential term has the base, and t, which is the exponent. Okay, so b, you might hear me call out the base. It's also the multiplier when we get into some of these application problems. Now, when we get a little more specific, this base of b, or the multiplier, is going to take one of two forms. When we have exponential growth, that value of b we're going to find by taking 1 plus r, where r is the growth or decay rate, or 1 minus r if it's decay. This r being the growth or decay rate, it's usually going to be given as a percentage. Okay, so we always want to take that value of r and write it as a decimal or a fraction. Fractions would be okay. But if it's a percent, we have to do that conversion. Okay, and that's something we'll work on here in just a second. Then this 1. Okay, a lot of times we don't really think about why that 1 is there. That 1 is there to represent 100%. Okay, or one whole of whatever it is that we're either adding to or subtracting from. So a quick example of this is, let's say you've got $100 and you get 5% interest on that $100 every month. Well, after 1 month, you're going to gain $5 and now your total is $105. So the growth rate there is 1.05, where you're keeping the 100% of the initial amount you had and you're just adding on that 5%. It works the other way for when it's decay. Okay, if I'm losing 5% of that $100, well, now I'm going from $100, I'm losing that $5, so now I'm going to have 95. But I'm still keeping my initial 100% and just losing that 5% on top of it. So this 1 is always representing the initial 100% of wherever we're starting from. All right, so we're going to build equations in all three forms here. Again, know that this is the equation for everything. Just sometimes the value of b gets split up to be 1 plus r or 1 minus r. All right, and the first thing I want to remind us about is if we're given a percent, because a lot of these problems do deal with percentages, this percent needs to be converted to a decimal. We've done this before, where if you take a percent and divide it by 100, that gives you the decimal version. Now, there's a shortcut to doing all of that. Okay, and I'll get to that in a second. Okay, but if I take 4% and divide it by 100, that's 0.04. So 4% is really 0.04. And a quick way to do this is I'm just moving the decimal place. When you divide by 100, that has you moving the decimal place 2 to the left. So if I move that 2 to the left, I have this gap right here. I'd throw in a 0, giving me that 0.04. Okay, 6.23, if I move the decimal 1, 2 to the left, I get 0.0623. 19, if I move that decimal to the left, 1, 2, I get 0.19. And then 47.6, 1 to the left, I get 0.476. So when in doubt, divide the percent by 100. The quick way of doing that is move the decimal to the left. If you're multiplying by 100, you move the decimal 2 to the right. So go the opposite way. Okay. And the last thing before we jump into some actual applications here is that if you're given an equation, can you decide, does that equation represent growth or decay? And it all depends on what that multiplier is or what the base is. Okay, so growth is going to happen whenever that base, so when B is greater than 1. Okay, so if our multiplier or our base is greater than 1, we have exponential growth. You're going to see me write this as B being greater than 1. Okay, as an inequality. For it to represent exponential decay, that base, or B, or the multiplier, is between 0 and 1. And the way that you're going to see me write that is as an inequality. This is saying B is greater than 0 and B is less than 1, or between 0 and 1. Okay, and that's a fancy way of saying that B is some decimal or some fraction that is smaller than 1. Okay, but it's going to always end up being positive. All right, so the only thing that I care about in the equations is the number being raised to the exponent. So in part A, that's the 2. This value of 2, so B equals 2 here, that is greater than 1. Since it's greater than 1, this means that we have exponential growth. Okay, so quick, easy thing to decide if we have exponential growth or decay. But you do need to understand what that base needs to be for it to represent growth or decay. Real quick, everyone decide if B, C, and D represents growth or decay, and give me the reason why. Okay, can you tell me why it's growth or decay? It should take about 1 minute. All right, thank you. All right, part B. The multiplier, the base is 0.97. That is between 0 and 1. Thus, we have exponential decay, or that equation is representing decay. C, same idea. Base is 0.75. That's between 0 and 1. So once again, we have exponential decay. And the last one, D, 1.089 is greater than 1. Excuse me. Since it's greater than 1, that means we have exponential growth. Okay, and that the whole reason for that is how exponents grow. If you look at, and I can show this on a calculator, but like let's say I take 0.97 and I start raising it to exponents, it's going to get smaller. 0.97 to the power of 5, 0.858. And if I keep raising that exponent, okay, it just keeps getting smaller. As opposed to thank you. As opposed to having a base that is greater than 1, if I start raising it to exponents, it's going to keep getting larger. Okay, so that's why we focus on that multiplier to decide if it's exponential growth or decay. Okay, well, let's flip this over and let's start going through some of these applications. And on top of money being really common applications with these problems, population is another kind of subgroup of problems that get applied to exponential growth and decay. The wording in all these is going to be a little bit different. Okay, sometimes we'll be given a percentage, sometimes we'll be given just the way that they grow in words. So we have to decide, what does all this mean? So it says scientists accidentally created 10 zombies in a lab and started a zombie apocalypse. They predict that the population of zombies will quadruple every day. That's a scary idea if that's a real thing, and you're about to see why. Okay, so first, is this exponential growth or decay? Well, if we're gaining more zombies, it's definitely growth. Okay, so I know I have growth. The initial amount, that is always stated in the problem. I don't need to do anything to figure that out. Okay, that's just 10 right now. Now the growth rate. Again, this is going to be the hardest part that we need to figure out because it gets communicated in different ways. If we are quadrupling, to quadruple means to multiply by 4. So multiply by 4. So that means that our growth rate is 4. Well, it'd be 4 to the power of x when I put it in the equation. With the equation, we need exponents here. Okay, to quadruple, it's going to be to the power of x. And so now, piecing all this together, we're writing the equation in the form of y equals a times b to the power of x. A is that starting amount of 10. So y equals 10. B is the multiplier, which is 4, and then to the power of x. So 10 times 4 to the power of x represents how this zombie apocalypse is going to break out. So now to answer our question, how many zombies will there be after 12 days? Well, x is our time, so I'm going to do y equals 10 times 4 to the power of 12. Right now, why don't you all grab a calculator if you don't have one already? Pause the video for a second. We want to make sure that we are able to plug this into the calculator and get the same value as me. So everyone should have the same buttons. Where those buttons are is going to be different from calculator to calculator. So I'm starting with 10. Then I'm going to put the 4 in parentheses, and that part is so important that we have that in parentheses. Then we're taking it to the power of 12. So to change the exponent, you're looking for this button that's like an upwards arrow, okay, called the caret button. So if I press that caret button, now I can type in any exponent I want, power of 12, and we get a huge number. We get 167,772,160. So if the zombie apocalypse broke out this way, in 12 days, we'd go from 10 zombies to 167,772,000. Yeah, we're toast if that happens. We have no chance. We have no chance. All right. Let's bring attention back up here. Shh. And before I move on from here, shh. Again, we need to stay focused. All right, before I move on from example 2, any questions with how I'm setting up the equation or how I'm getting this value? Okay. Example 3 works out a little bit differently. And again, it's all based on how that multiplier or the base is being communicated, our growth or decay rate. So it is estimated there are $25,000 or dollars, 25,000 polar bears. Okay, that's our initial amount, the 25,000 polar bears. Their population declines. That word declines is telling us that we have exponential decay. So we should end with a lesser amount than what we started with when we actually get to the calculation portion here. They're declining by 1/4 each year. So again, when we think about what this rate needs to be or what our base is going to be in the equation, it basically represents how much is sticking around. If we're losing 1/4 of the population, how much are we keeping? Well, one way to figure that out is to take that 1 minus the rate. So 1 minus 1/4. And what's 1 minus 1/4? Oh, okay. Yeah, think of if you've got a big pizza, you cut into 4 slices, you take 1 away, you've got 3 left. You've got 3/4 left, which is 0.75. And so if we're losing 1/4 of the population each year, that means there's 0.75 or 3/4 of the population that sticks around. Okay, so that's what we're always going to use in the equation. How much are we keeping? How much are we going to move forward with? And that's going to be 0.75 of that initial population. So our equation is y equals 25,000, then 0.75 to the power of x. Always to the power of x. All right, then to the nearest whole number, how many polar bears will there be left in 5 years? So I'm going to plug in 5 for x. It's 25,000. And then 0.75 to the power of 5. And again, we'll just plug that all into the calculator. .75 to the power of 5. And I get 5,932.617. That's telling us to round up. We'd have 5,933 polar bears left after 5 years. Okay, which is quite a lot, right? If we're starting with 25,000 and 5 years later, we're now down to just under 6,000. It's quite a few that decline. Okay, we're going to do one last problem together. I'm going to have you all do example 5 on your own, and that should take us right to the end of class here. All right, example 4. Now the rate is being communicated as a percent. Okay, so a little bit different here. So the number of students enrolled at the college is 15,000 and it grows 4% each year. That initial amount's easy to identify. That's the 15,000. Growth or decay, this is growth. And then the rate, we need to take that percent and we need to convert it to a decimal first. So 4% as a decimal is 0.04. And then again, we want to think about how much are we moving forward with? We're not moving forward with just 4% of that population, right? We're keeping the initial 15,000 and adding 4%. So that's where we're going to take the 1 plus 0.04, which equals 1.04. So 1.04, telling us that we're growing by 4%. So the equation, y equals 15,000, 1.04 to the power of x. So 15,000, 1.04 to the power of 25. So 15,000, 1.04 to the power of 25, and that is 39987.54. If the problem doesn't say how to round, then I'm not going to be super picky about it. But typically, it kind of depends on what it is that value represents. If it's something to do with populations, decimal populations don't make a whole lot of sense. Okay, so we're just going to follow typical rounding rules to the whole number. Okay, so we'll add, or we'll round that up, so that would be 39988. It's 39,988 students. Okay, so it's more than doubled in 25 years, okay, which is quite a bit. All right, let's do like 2 minutes to go through example 5, and just do that in your groups. Again, all I ask is that you try. It doesn't need to be perfect. And it's the last thing we got today. All right, so your equation. And the main piece of this, again, is how we are communicating how much we're either decaying or growing by. Okay, we're losing 2% each year. Again, in our equation, the value of our base needs to be how much is sticking around. How much are we keeping? Well, if we're losing 2%, that means 98% of the population is sticking around. Okay, so you need to do the 1 minus 0.02. Again, that is the most common thing that we're going to mess up here is forgetting about that 1. If we're gaining or losing a percent, it's all from the initial 100%. That's what that 1 is representing. So 45,000.98 to the power of x. Plugging in 15, I get 33,236. So it declined by about 12,000. Okay, or roughly 12,000. All right.